Ever wondered how major online services keep working, even when parts of their system are failing? Today, we're diving into the essential concept of graceful service degradation. It's about designing systems that bend, not break, ensuring a consistent, albeit sometimes reduced, user experience. By the end of this lesson, you'll gain practical skills to build incredibly resilient applications. We'll start by understanding how systems maintain core functionality even under extreme stress. Then you'll learn to implement powerful patterns like circuit breakers and various fallback mechanisms to prevent cascading failures. We'll also explore smart strategies like load shedding and health-aware routing that adapt to changing system conditions, protecting your most critical features. Finally, we'll cover the often overlooked aspect of observability during degradation, so you can truly understand how your system is performing when things get tough. Get ready to master the art of building systems that are robust and reliable no matter what. Imagine your favorite streaming service during a spotty internet connection. It doesn't just stop, it might switch to lower quality, buffer more. That's graceful degradation in action, and it's not a simple on-off switch. Instead, graceful degradation is a spectrum. Think of an e-commerce site during a massive sale. It might first disable personalized recommendations, then customer reviews, but the core ability to add items to cart and check out remains fully functional. This approach prioritizes what absolutely must work, gradually shedding less critical features as system load increases or components fail. The goal is always to maintain a usable, albeit sometimes simplified, user experience. You're giving users something that works rather than nothing at all. It's about being smart with your resources and protecting the most vital parts of your application from cascading failures. This philosophy is fundamental to building truly resilient systems. Just like an electrical circuit breaker protects your home from overloads, a software circuit breaker protects your microservices. It's a critical pattern for preventing a single failing service from taking down your entire system. The circuit breaker pattern acts as a digital safety net. When a service starts experiencing problems like timeouts or errors, the circuit breaker trips, preventing further requests from reaching that unhealthy service. This isolates the issue and allows the failing service to recover without being overwhelmed. It operates in three key states. Initially, it's in a closed state, allowing all requests through while monitoring for failures. If a failure threshold is met, it transitions to an open state, immediately failing requests and returning a fallback response, protecting both the client and the struggling service. After a cooling-off period, it enters a half-open state, cautiously allowing a few test requests to see if the service has recovered. If these succeed, it closes. If not, it reopens. This fail-fast mechanism is crucial for maintaining system stability and quick recovery. What happens when a critical service fails, even with a circuit breaker in place? You need a plan B, C, and even Z. That's where fallback strategies come in, ensuring your system can adapt and continue providing value. Resilient systems don't just stop, they have multiple layers of fallback. First, there are static fallbacks, which are pre-computed responses cached locally. If your recommendation engine goes down, you simply show a list of popular items instead of personalized ones. It's quick and requires no external calls. Next, we have simplified logic. During periods of high stress, you can temporarily strip out complex features. Think of an e-commerce site during a flash sale. It might disable address validation or gift options to ensure the core add-to-cart and checkout flow remains fast and reliable. Finally, cross-service fallbacks involve routing traffic to alternate, perhaps less sophisticated implementations. For example, a photo service might fall back from advanced AI tagging to basic metadata search if its machine learning services are overloaded. The user still gets results, just not the enhanced ones. These strategies ensure core functionality persists even when supporting services struggle. So, how do the tech giants actually put these ideas into practice? Well, companies like Netflix, Amazon, and Google are masters of graceful degradation, often without users even noticing. Netflix, for instance, uses adaptive bitrate streaming, downgrading video quality before buffering, and content pre-positioning to serve cached content when CDNs struggle. You might see slightly grainier video, but it keeps playing. Amazon, during events like Prime Day, employs sophisticated load shedding by prioritizing requests based on customer value. A user checking out gets priority over someone browsing a wish list. They also use feature toggles to disable non-essential functionality like product comparisons. Google Search demonstrates nearly invisible degradation, serving slightly stale results faster or simplifying spelling corrections, making trade-offs users rarely notice. For your own systems, you can implement health-aware load balancing, which intelligently routes traffic away from struggling services, and don't forget request prioritization, ensuring your most critical paths always succeed during stress. These patterns are not just theoretical, they are the backbone of resilient systems in production today. You've implemented all these clever degradation patterns, but how do you know if they're actually working as intended? This is where observability becomes absolutely critical, especially when your system isn't at 100%. During degradation, traditional success rates might look good, but the user experience could be suffering significantly. You need to look beyond the obvious. First, monitor feature utilization rates in degraded modes. If 80% of your recommendation requests are now hitting a static fallback, your primary ML service clearly needs attention even if the user isn't seeing an error. Next, track fallback activation frequency and duration. Your circuit breakers should trip under stress, but they should also recover quickly. If they stay open for hours, you have a fundamental problem. Most importantly, measure user journey completion rates across different degradation levels. Can users still successfully complete a purchase when payment processing is degraded? This holistic view tells you the true impact on your business. Focus on how quickly your system recovers to normal operation. These deeper insights help you fine-tune your resiliency strategies. We've covered a lot today, from understanding the degradation spectrum to implementing advanced patterns. Let's quickly recap the key takeaways that will empower you to build more robust systems. First, remember that graceful degradation is about building systems that bend, not break, ensuring core functionality remains available even when things go wrong. We learned how circuit breakers act as digital safety nets, isolating failing services and preventing cascading failures, while fallback mechanisms provide essential Plan B through Z options, from static responses to simplified logic and cross-service routing. We also saw how tech giants like Netflix, Amazon, and Google apply these principles through adaptive streaming, load shedding, request prioritization, and subtle degradation to maintain user experience at scale. Finally, we emphasize the importance of observability with specific metrics that truly reflect system health during degraded states. Now for a quick self-assessment. How would you handle a critical payment service outage during peak traffic, ensuring customers can still complete their orders? Think about the patterns and strategies we discussed today. Your answer should involve isolation, fallbacks, prioritization, and clear user communication. Keep these principles in mind, and you'll be on your way to designing truly resilient systems.